Okay, here's our starter problem. There are 100 people in line who are numbered 1 through 100. You want to choose the first 4 people who have numbers that are multiples of 9. List the numbers that correspond to these 5 people. Okay, so we're looking specifically at multiples of 9. So we're going to start with 9, of course, would be the first person that comes in that is a multiple of 9. And then just listing them, there's just multiple. 9 times 2 would be 18. 9 times 3 is 27, and 9 times 4 is 36. So what is this? Numbered in line, right? So the 9th person in line, 18th person in line, 27th person in line, and 36th person in line are the first 4 multiples of 9, people in line that are numbered, I guess. So that's how that works on this one. I know it goes up to 100. So, I mean, you could go up as high as, 99, the 11th multiple of 9, but we don't need to go that far. Just ask for the first 4. Okay, there's our objectives. So I know the different parts of fractions and mixed numbers. I can write fractions and mixed numbers from shapes, and I can change mixed numbers into improper fractions and back again as well. So here we got fractions. Remember, it's this part of the division, but fractions are all division. As it turns out, we've been looking at it as dividend divided by divisor. So we'd say the top number is the dividend. Bottom number is the divisor, and it's really asking how many 2's in this specific example, how many 2's are in 12. Fraction is shown the same way, and you get the quotient, how many divisors are in the dividend, but the vocabulary is going to change now. Okay, the top number is now going to be called a numerator. The denominator is the bottom number. Of course, what this equals is still a quotient if you do the division. But from here on out, we actually are not going to be looking at this with long division. And yeah, formally, fractions can't have decimals in them, or really other fractions as well. What we're going to do is we're going to take these fractions like this one, and we're going to do what we call simplification, which may result in a new fraction, but it will look a little different, but the value overall will still be the same. And that's something we need to understand. This goes back to what we talked about before. Math is what we need it or want it to be. Sometimes we don't want a specific fraction, but we want it to have the same value, but to look differently. Okay, maybe we're splitting up into other parts, right? So 12 divided by 2 is the same thing as 24 divided by 4. So maybe you got 12 pieces of pizza that you could split up between 2 people. But if you wanted to split it up with 4 boxes or 4 people, then you'd have to double the amount of pieces. So you'd have to cut each piece in half and then divide it by 4 kind of thing. Okay, so again, what do you want? What do you want the fraction to look like? What is the purpose of the fraction and the division? And that should help you to determine what kind of new fraction that you want. So fractions, though, of course, you got dividend and divisor, but now with numerator and denominator, the numerator really tells you, and I relate this to pizza, which I'm reluctant to do with, what time our class is, but the numerator tells us how many pieces there are. The denominator tells us how big the pieces are, okay? So, for example, 12 over 2 tells you have 12 pieces that are, we would call that a half-size piece, okay? So 12 divided by 2, again, you could make it fourths. You could say it's 24 fourths, and you have the same amount of pizza, but now since you split it into fourths, you've made the pieces smaller. So really, the bigger the denominator, the smaller the piece. The smaller the denominator, the bigger the piece will be. So let's start with these 2. These are 2 fractions. We just want to know that you know where numerator and denominator is. Now the numerator, of course, is the top part of the fraction. The denominator is the bottom part of the fraction, which we can call the numerator a dividend and the denominator a divisor. It doesn't really matter. But here, on this fraction, 4 over 7, 4 divided by 7, however you want to read that right there. But I know that the numerator is the top number. So I simply label the top 4 as the numerator. Again, that tells me how many pieces I have. Again, I would be thinking of a pizza here. And then the denominator tells me how big the pieces are. So the bottom number is the denominator. So you have 7th size pieces, but you only have 4 of them in whatever pizza it is that we're looking at. Now this one, it's kind of ridiculous to think of numbers that big, but the idea is the same. The top number is the numerator now. It's still a dividend, but it's a numerator now. And then the bottom number is the denominator. There we go. And that's all you need to do for problems like this. So just be aware you're going to have to do this on the assignment. There you go. So we got this, I guess we can call it pie chart, but it says circle. What fraction of the circle is shaded blue? So we're expecting a fraction. So there's my fraction line. I got my numerator in the top, denominator in the bottom, just like it shows it set up here. We're not concerned about the quotient right now. So looking at shaded blue, okay, so I would look and just count how many pieces are shaded blue. 1, 2, 3, 4. So we know how many pieces is the numerator. How big they are is the denominator, but which tells us how many pieces it takes to make it a full circle, I guess, in this case, or you could say it's a pie. But since we've already counted 4, this would be 5, 6, 7, and there's 8 pieces, meaning they're size 8th pieces. This would be 4 pieces shaded blue out of, and there's 8 pieces in the whole. I guess we counted them clockwise here. So 8 pieces, that's our denominator. 4 of them are shaded blue, that's the numerator. So you can go both ways. Some of you may have counted all the pieces in the circle, made that your denominator, and then counted the blue pieces, and then put that in your numerator, which is just, it just reverses the way that we did it. But again, you should get the same answer either way. Now, some of you may be looking at this fraction and you could simplify it. That's okay if you can. We're not worried about that right now. We just want to be able to write a fraction based on a scenario. Sometimes they'll make these rectangles or some other shape, doesn't matter. Again, you could just count how many pieces are shaded blue and then how many total pieces there are. Okay, on this one, I'm going to do it the same way, meaning here I'm going to make a fraction. I'm first going to figure out what my numerator is, and it's saying what fraction of the circle is shaded blue. So I'm looking at those blue pieces. How many are shaded blue? 1, 2 pieces. Okay, so I have 2 pieces that are shaded blue out of how many pieces? 3, 4, 5 pieces, right? Because we've already counted these 2, but there's 3 more pieces to make it 5 total pieces, meaning the sizes of the pieces are 5th size, and 2 of those 5th size pieces are shaded blue. So a mixed number takes on this format, okay? You have a whole number and a fraction. And the fraction still remains numerator over denominator. Numerator on top, denominator on bottom. The whole number, though, tells you how many full pieces there are. So in the last 2 examples, we were looking at a circle, and they were split into fifths in the last example. And 2 examples ago, it was split into eighths, which would have still defined the denominator, okay? So when we look at these, we're looking at, when we fill in the fraction, you're still looking at how many pieces, I guess, are shaded, or whatever the scenario is, in the top. And then in the bottom is how many pieces total are in the shape, okay? But the fraction part of our mixed number it's kind of like the last shape that is not fully filled in. Some of it may be filled in, some of it should be filled in. But then you have the whole number. The whole number tells you how many full pieces are shaded. So mixed numbers is the combination of the whole number and the fraction that represents the full value right here. But yeah, it's saying here in the mixed number, the numerator is still the top number, which is just showing this in an abstract way, B over C. Okay, so A is our whole number, B is the numerator, C is the denominator. This is the format that we're looking for. So here we have these 2 numbers. I'm going to read them, 8 and 5/6. This one would read 1 and 17/200. And let's start with the 8 and 5/6 right there. So the 8 there, it's the number not in a fraction, which means it has to be the whole number. The 5 is the top number in the fraction, so it must be the numerator. And the 6 is the bottom number in the fraction, so it must be the denominator. That's it. Okay? So let's do this other one as well. Try not to overlap it, but they still might, and that's okay. So here, 1 is the whole number. Okay, that's a little better. 5 is the numerator. I'm sorry, I was looking at the last one. In this one, 17 is the numerator because it is at the top. And where we have 202 in the bottom, that'd be 200 seconds, I suppose. That will, since it's in the bottom of that fraction, it becomes where it is already, our denominator. So that's all we got to do on these. Just identify the parts of the mixed numbers. But they're mixed because you have the whole number and the fraction. So here's rectangles, right? We're not looking at circles anymore. But one big rectangle will represent one whole. Okay, so we got whole pieces that are fully shaded in. And it's saying to enter your answer as a mixed number and an improper fraction. We're not worried about the improper fraction right now. We'll get to that because we haven't gone over improper fractions yet. But the mixed number, though, so we have the whole number. And I'm just going to kind of put boxes out here for us, okay? So you're going to have the whole number here. And then you're going to have your numerator here. And then your denominator here. And yeah, those boxes aren't quite the same size, and that's okay. But that's a fraction, so there's my fraction line. I just got to fill in the boxes. That's it. So the whole number is how many full, in this case, rectangles there are. So how many full rectangles are there? Well, you can count them. I got 1, 2, 3, and 4. There's not a fifth full rectangle here, but this will represent our fractional part. So I counted 4 full rectangles. Okay, now over here with this fraction, the numerator, so the fraction has to do with this remaining part, right? It's not a full rectangle, it's not fully filled, but the numerator is how many pieces in this case are shaded gold. The denominator is how many pieces are in the shape. So how many pieces are shaded gold? I count 1, so that will be my numerator, 1. It's in the top. How many total pieces are there? Well, we already counted 1, then there's 2, 3, 4, and 5, meaning the sizes of the pieces are in fifths. Then that must be our denominator right there. Okay, now that's kind of how it usually works on the assignment. You just kind of fill in those boxes. But if we were to write this as a mixed number without the boxes, you'd see something like this, 4 1/5. Okay, in fact, I kind of made this line a little big, and that's okay. So these are the same. I'm just showing one with the boxes that you may have to fill in on the assignment. This one is without the boxes, okay? But the scenario we started with, it was 4 full shaded boxes, that's the 4, and then we had 1 piece shaded out of 5 pieces, 4 1/5. All right, how about this one? Well, we want to write this as a mixed number, but it's based on the circles now, right? So it says that one circle represents one whole. So for our mixed number, okay, let's go ahead and set this up. I got my fraction line. Just to the left of it will be bigger than the numbers in the fraction, but that's my whole value. That is how many whole pieces there are. And how many whole pieces are there? Well, we count 1, 2 full circles, okay? So in my mixed number, it's 2 and some fractional value. So in the numerator, I would count how many boxes, or in this case, slices, I guess, are shaded blue. There's 1. So it's 2 and 1 something. We don't know what the denominator is yet, but we can count 1, 2, 3, 4, 5, and 6. So 6 pieces, it takes 6 pieces to make up a full circle, which is true for these other ones as well. And so we make it 2 1/6. That is all. So proper and improper fractions. For regular fractions, actually proper or improper, you have a numerator in the top, a denominator in the bottom of your fraction. The answer is a quotient. We're not worried about quotients yet. We'll get there. But a proper fraction is where the denominator is bigger than the numerator. Now you can switch this and say that the numerator is smaller than the denominator, and that would be fine as well. But an improper fraction is where the numerator is the bigger number. Okay, so the top is going to be a bigger number than the bottom, which is the denominator. Again, you can reverse this and say the denominator is smaller than the numerator. Doesn't matter. But once you get these conditions, if the denominator is bigger, it's a proper fraction. If the numerator is bigger, it is an improper fraction. That's it. So that's some vocabulary we have to remember, because we're going to be making these statements. You know, we're going to look at a fraction, then we can declare if it's proper or improper. Now, in examples, like we're going to be seeing here shortly, we will know if a fraction will need to be improper if you have more than one whole of something, right? Like in the last example, what do we have? We had some circles, and then they were shaded blue. So there was one full circle, and then there was another circle, you know, that was split something like this, and maybe it's got a couple pieces shaded. And this is just a different example, but the moment I see a full circle shaded in, or it could be a rectangle, and then I see some other parts shaded in, is the moment I'm looking for an improper fraction, because it can be shown as a mixed number. That's important to remember as improper fractions. Improper fractions are just a different way to show mixed numbers. And again, it's like, well, what are you trying to get out of it? And that's where we say, well, it depends. And math can be whatever you want it to be. So we leave it up to whoever's doing the math to make the interpretation, or find out if they want to show an improper fraction or a mixed number. And this is a perfect example with it, right? So we've seen this one already, and the last one we did this, it was a mixed number. Since I'm seeing whole rectangles filled in as gold, then I'm expecting this to be an improper fraction. It says, well, what is your improper fraction? Well, I would expect it to be an improper fraction because I already had some whole values filled in. So the fact that they're saying make it an improper fraction is kind of a redundancy, because we see that the diagram already came with full rectangles filled in. All right, now I'm going to start with the denominator with my improper fractions, because that will tell me how many pieces are in each whole. So we can count these. So that'd be 1, 2, 3, 4, 5. We've already counted those already. So you may have known already that our denominator, that's the sizes of every piece, even the ones that are already filled in, right? They're fifth size pieces. You can count. Each one of these bars has 5 pieces in each. Okay, now the numerator tells us how many of those pieces are shaded, in this case, gold. Now you can count them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Maybe a better 9 than that. 19, 20, and then 21. So that's all the pieces that I counted that are shaded gold. So as an improper fraction, this would be 21 fifths. Now I'm going to show this, the mixed number that we already had, and then we're going to kind of think about the relationship between these, okay? So this was 4 whole pieces, and then there was the extra 1 piece out of the 5 pieces, 4 1/5. This one, there was 21 pieces filled in gold out of, again, the sizes were fifth size pieces. The question would be, how do you change a 4 1/5 to a 21/5? Or how do you change a 21/5 to 4 1/5? Well, we'll get into that. Not yet, but I just want you to think about the relationship there. How would you make one the other? Here's our other example with the circles. But we're looking for the improper fraction on this one. So here's my fraction. Now again, we did already count the pieces. So this would be 1, 2, 3, 4, 5, 6 pieces in each circle. So I'm looking at 6th size pieces. That's my denominator. And again, I always start with the denominator in my improper fractions, but you can start with your numerators. Now I just got to count the pieces, and it doesn't even matter where I start. I could start with this one piece here, 1. I'm not going to, but you could, okay? So I'm going to start over here, 1, 2, 3, 4, 5, 6. Okay, now we expected there to be 6 here because there was 6 in this one as well. There should be 6 here. And again, that I'm kind of showing that you could make this repeated addition, which is multiplication. I've already counted 6. That's 7, 8, 9, 10, 11. There's 12 pieces. And then finally, the last one that's shaded blue makes 13. Now I just want, again, let's go back and relate this to the mixed number that we already saw for this one, which would have been 2 1/6. Okay. So let's dive a little bit deeper than this one than to just say, well, think about it, okay? So these two pieces, this had 6 pieces, this had 6 pieces. That would have been 12 pieces, right? Well, the 12 pieces comes from the 2 holes right there. The 2 holes in our mixed number represents 12 shaded pieces. Okay, now you say, well, there's 13 pieces out of 6, 13 pieces in 6 size pieces. Okay, so we had the 12, then we add the 1. See that? 12 pieces plus the 1 makes the 13 pieces in 6 size pieces. So that should help us at least to go from mixed numbers to improper fractions, hopefully a little bit. Okay, because that kind of is the process to change a mixed number into an improper fraction. Improper fractions to mixed numbers require some long division, which we'll get into. Okay, so we're just going to look at these numbers. We're going to identify them as either proper fractions, improper fractions, or mixed numbers. Now, for me, it's easier to start with mixed numbers just because visually I can see already that we have whole values with fractions between these two. So I don't really need to see the fractional part of it. I just know that it is a mixed number. Okay, so 5 2/3 is a mixed number. But in addition to that, 7 2/5 also is a mixed number. So those two are done, but let's go to these fractions, okay? So here we got 3 over 5. And in this case, the denominator is bigger. So if the denominator is the bigger number, then we are looking at a proper fraction. So I'd say down here, 3/5 is a proper fraction. Then we look at 10/5. Now the numerator is the bigger number. Okay. If the numerator is the bigger number, then it becomes an improper fraction. So we'll put this label over here. That's it, right there. So that is just identifying each of these. We're not asking for any conversion. We're not asking you to make any kind of diagrams to represent them. We just want you to know, we want to know that you know how to identify these as either a proper fraction, mixed numbers, or an improper fraction like this. Not just because you're going to have to do this on the assignment, but because, just out and about, you may see these types of values, and then you'll know if it's a mixed number or an improper fraction. Okay, so this one, mixed numbers and improper fractions, we're looking to be able to change an improper fraction to a mixed number. We'll go the other direction, but first this one. So the quotient, what we're going to do here is we're going to use some division, right? Because that's what the fraction line is. We're going to use long division. When we get the quotient from the long division, that will be the whole number. The remainder ends up being the numerator, and the denominator just stays the denominator. So if you have any fraction, improper or proper, well, improper, I should say, an improper fraction, if you're changing it to a mixed number, the denominator will stay the same. Now, I'm going to show this a couple times, and I'll use kind of like a diagram modeling situation to demonstrate what's happening here. So it's saying that you got 37 pieces that are 1/8 size pieces. But in addition to that, and it's kind of in the statement as well, but the 1/8 size pieces tells us that it takes 8 pieces to make a whole, I guess, whatever the shape is, okay? So 8 pieces makes a whole. We can just state it like that. So every 8 pieces that we get from the 37 will make a whole. So again, if we look at this in the form of a diagram, we'd have 37 pieces. Now, this is 37 1/8 size pieces. What makes these an 1/8? Well, here's what makes them an 1/8, is that if I look at these, and I've done this on purpose, by the way, so it may take some work otherwise. But I'm going to look at this first row, let's call it a row, and if I were to box these in to make one full unit, I guess, that is one full unit, okay? Now, what happens, though, is that I've got one, two of them, there's another one, and then I got a third one, and then I have a fourth one, like this. Okay, so this means that 37/8 will have 4 whole units in it, and then what do you got left over? Well, you've got the 5 left over here. 1, 2, 3, 4, 5. 5 pieces left over. So that's my numerator. That's how many pieces there are, but the sizes of the pieces haven't changed. It still takes 8 pieces to make a whole unit. So that's one way to do it with the diagram. Of course, it becomes a little unpractical with however many pieces there might be. Like the numerator, if it's large, drawing it out like this may not be very practical. But since we're looking at this, it's 37, and let's change this back into a division problem, so we can relate it to division, which is what we're trying to do. 37 divided by 8. Okay, so we can put this into context as well. The question it's asking is how many 8s are in 37? But more specifically, how many, in this case, because we're talking about the sizes of the pieces, 8s are in 37 pieces. Okay, so there's our question mark. Which is why it becomes a division problem like this. So, in order to work with this information that we have, then I would take 37 and divide it by 8, where I know the quotient will be that's going to be my whole value in the mixed number, and the remainder will be the numerator. So let's show this, just to show that it works. Now, we've shown it kind of with the modeling like this, and maybe it helps, maybe it doesn't. You can just do straight division, which is this division translates into this other division, which translates then into long division. Do you need to show that always? No, but again, the long division hopefully will help us to see how many 8ths are in 37. So again, 8 pieces makes a whole. So right here, I know that 8, it doesn't go into 37 evenly, but you can do it 4 times. Okay, so we're using up 4 times 8, which is 32, means that we're using up, in this case, 32 of the 37 pieces, which gives me a remainder of 5. So that is why we have 4, remainder 5, and then again, the denominator is just whatever the dividend is, and in this case, it's an 8, so we keep it an 8, that's it. So long division is how I'm going to be doing this in the future. I won't be showing a lot of modeling like this, but long division is usually how I show how to make or change a improper fraction into a mixed number. So that's what I'm going to do on this one. I'm going to use some long division here. Okay, now my numerator, it goes where the dividend goes in long division. That's inside the long division symbol. And then the denominator is the the divisor, so it goes on the outside. Now 3, it doesn't go into 2, and you're welcome to put a 0 there if you'd like, but I know that 3 goes into 25, because now I look at it as a full value of 25, it'll go into that 8 times. Now I'm going to keep the 0 there. I made it smaller on purpose just because we don't need it, but we need something to hold that place value. So how much of the 25 was used up? Well, I do 8 times 3, which is 24, meaning we're using up 24 of those pieces, and then this, when I subtract that out, see what's left over, that's my remainder. 25 minus 24 is 1. You can just say 5 minus 4 is 1. Okay, so I'm ready to change this into its mixed number. So my quotient is 8, and then in the fraction, you still have a denominator of 3, but the one remaining is the numerator. And that's it. So mixed numbers and improper fractions, I use what I call cycle method. This is not academic. It's like if you went to a teacher and was like, "What's cycle method?" They wouldn't probably know what it is because I just kind of made this up because it looks like a cycle, right? Now, it doesn't fully cycle. You go from A to C to B, and this is the operations. You have to do it in this order specifically, not because of the order of operations, but it's because this is how mixed numbers work. You take the whole value, you multiply it by the denominator, whatever that product is, then you add the numerator. So it's kind of given in formula format down here. If you know what these numbers are, you can kind of replace these into this formula and then solve for it. So this is what you're going to expect: multiplication, then addition. That just gives us a new numerator. Again, the denominator will still be the same. So even when you get the improper fraction out of this, whatever the denominator is, in this case C, it just stays that way. And then whatever we get from this operating cycle method, that's what we put into the numerator. Now there's a reason for this though, and that takes us back to this example which I was trying to show earlier. So remember this one, how as a mixed number, we had 2 1/6. So we had the two wholes here, right? You've got the one whole and then the second whole. But again, it'd be like, well, how many pieces does that make? Well, because we're looking at the denominator, that tells us the sizes of the pieces, or how many pieces make a whole. It was 6 pieces. So again, you'd have 6 here, 6 there, and you got, in other words, this is the same as saying you have 2 sets of 6, which is 12, right? Now that's where the 12 comes in here. That's the 12 pieces. But then what do? Then you add the 1 to the 12, and that's how you get the 13 right there. Because, and this one is this piece here. It's the 13th piece. So, again, I just want to reiterate this. You got a full set here of 6, another full set of 6. That's 6 times 2, which is 12, and then plus the 1 that is left over because we don't have another full shape right here, full circle. So that's why we use cycle method. And again, just to emphasize what we were talking about here, if we're looking at ninths, each of these 11, we'll just say circles or pies, each of the 11 circles is split into 9 pieces. So the 11 right there, the whole value, tells us essentially that you have 11 sets of 9, or you could say ninths. All right. Now the reason why that's important is because now 11 sets of 9 is the same as taking 11 and multiplying it by 9. So this is how many pieces would fit into the 11 shapes, or in this case, we're relating to circles. 11 times 9 is 99. So that's 99 pieces just from the 11 full circles. But then what do we got? Then we have this 5 that's left over. Remember those 5 pieces right there? And that's why we add the 5 to the 99 to get us a new numerator, which would, I'm skipping some work here, but you would get 104. Okay, so the improper fraction of this mixed number, the denominator is going to stay the same as 9, but my new numerator ends up being 104, and it's 104 of these 9s. This one, I'll try to be a little bit more thorough with this one. But again, our whole value here, the 4, that's 4 whole, you could say circles, we'll just say holes. Now, each of the holes is being cut into 2 pieces, right? So 4 holes, and there's 2 pieces for each hole. Now, it wouldn't be hard to demonstrate this with a model, so here we go. All right, so I have the 4 holes, right? There's 1, and then 2, and I know I haven't split these up yet. I will. Let's do this first. Let's see if I can get it to work. Okay, there's 2, and then 3 and 4. Now, again, each of these has been split in half, so we'll pretend like these are being split exactly in half, even though my drawing may not be very good at demonstrating that. Okay, so that's 4 holes, and you know what, I'll even shade them in there just to be extra thorough there. So staying within the lines was never my strong suit as a kid and when I was using crayons or markers. So again, please forgive the sloppiness of the drawing. But that's my 4 holes. Well, how many pieces is that? Again, you could just count 1, 2, the wrong marker there. 1, 2, 3, 4, 5, 6, 7, 8 pieces right there. Okay, and that's why we end up doing in cycle method, we would show this as 4 times 2. Okay, so there's starting here, I would have 4 times 2, which is 8. And that's the 8 pieces that we just found there. But then the cycle method would complete by adding the numerator there, 1. So I'd say 8 plus 1 is 9, and that is my new numerator for my improper fraction. So there's 9 pieces that are half-size pieces, so 9 over 2. Once again, we always just keep the denominator the same. Now, in the future, we'll look at this fraction. We will look to simplify it. But in other words, this is also telling us that, let's see if I can do this. We have the 4 full pieces. But what happens here is that you actually have another piece here, another whole, but it's been cut in half, and there's only one of the halves that we'll say is that would have been filled in. Okay, and that is where the 9th piece comes in. So hopefully that helps. Again, the diagram, I won't be using these diagrams anymore. It's just cycle method for me. And so, but I hope it makes sense why we do it. All right, graphs of fractions and mixed numbers, we just need to remember that the denominator tells you how many parts are in each unit, not how many lines, but parts. Which I have to keep in mind. Well, there'll be a pattern when we start breaking those up. The numerator tells you how many parts there are, and if you're looking at a mixed number, the whole value will tell you how many wholes are included. So first up, if you saw something like this, this is what it's going to look like on the assignment. It'll say graph 1/6. Okay. So what we need here is 1/6 size pieces. Now in the assignment, when it says partitions, it's talking about marks or markings, okay? Not how many parts are in each unit. So where it says 6, you don't want to increase this up to 6. What I'm going to do is I would push this 5 times, and then what happens is you'll get something that looks like this. Okay, now is this perfect? No, but on the graph you're going to see, it's going to look something like this. I just push this 5 times, and then it gives me each of these. These are partitions, or I call them markings here. Okay, well, why did I push it 5 times? Because we're looking for sixths, and you can see by pushing it 5 times, by making 5 markings or partitions, it gave us 6 parts. There's 1 part, 2, 3, 4, 5, 6 parts in each unit, right? So that from 1 to 2, there'd be 1, 2, 3, 4, 5, 6. 6 parts. All we want here is 1 of the sixths, okay? So each marking represents its own sixth. So this would be the first in a set of 6 or sixths. So we would put a dot right there. So what this means is on the assignment, you take this mark and then you drag it over here. And then, of course, that mark wouldn't be there anymore. It would be gone. Okay, and that's what we're looking for on these types of problems. Okay, so on this one, again, we look first at the denominator, which is 4. So that means we need 3 markings, and that will show that it splits up into fourths. So I push this 1, 2, 3 times, and then you get something that looks like this. You'd have these markings or partitions, something like this. All right. Now the whole value here, 1, means that you can kind of start here at 1, but then you need an extra 1 of the fourths. So see, 3 partitions made 1/4, 2/4, 3/4, 4/4, and then again, each of the units is split into 4 parts, even though we have only 3, we only have 3 partitions or markings. So you'd have the 1, and then you'd need the next fourth, which would be here. That would be 1 of the fourths. But again, it has the 1 as a mixed number. So we need to take this mark here and then drag it over here, and then it would look something like this, with the mark that's there, of course, being moved. Okay, that's it. So on this one, once again, we look at the denominator, which is 3. That means I need 2 partitions or markings in between. You'll see that splits it up into thirds. So I would push that partitions once, twice, and then I would have 2 partitions in between. But again, it makes up thirds because between 0 and 1, you have 1 part, 2 parts, 3 parts, and between 1 and 2, you have 1, 2, 3 parts. Thirds, okay? So each of those pieces would be its own third. What we need here is 7 of the thirds. Okay, so I can count each third if I wanted to. This would be 1 of the thirds. That's 2 thirds. 1 would be 3 of the thirds. And continuing, we'd have 4 of the thirds here, 5 thirds here. You know, keep these as improper fractions. Then 5 thirds would then be 6 thirds. Now you see the graph that I have is not long enough. I believe that they will be on the assignment, so I just need an extra marking somewhere over here. So I'd have to kind of extend that line, and that would represent 7 of the thirds. Each part is a third. We've counted 7 of them out, so I would take the point here that starts at 1, and I'd have to drag it over. And that's it. Now, one last note about this is I believe I saw something like this on the assignment where the line does not actually go to 7 thirds. If it gives you something like that, just click on new problem, or put something in and then just say, I want to try a new problem, and wait until you get something that will fit on the graph. Okay, right here we're asking how much of the orange strip is the light green strip right here. So that's all we're worried about on this one. So let me see if I can take these out, something like that. No, it's not perfect, but I'm doing the best I can with the technology. And we're going to compare that light green strip to this orange strip here. That one worked out okay. All right, so I would kind of line them up like this, okay? And then what I need to do is see how many of these green strips go into the orange strip. That'll tell us how many parts of green strips there would be to make an orange one. Now, of course, this isn't going to be perfect because of the way I'm using the technology, but hopefully it's fairly close there. So there's 1, 2, 3. And then what we see is that the next one is not going to be a full green strip, right? So if I put this over here, there's a little bit of, I would say, guessing involved here. Now, you could go to the actual program and do this, but what I've got to do is I've got to kind of transfer this line here upwards and see that extra part of the green, right? So it looks to me like if I were to split that into equal parts, that's going to be in thirds right there. So each of the green, I'm going to split into thirds. Okay, so I can see each of the greens is split into thirds because of this last portion right here that didn't make up the full orange, what do they call it, strip. So what I'm going to do as well is I'm going to transfer these down into the orange mark, including where they end. And then this will tell me how many pieces it would make up. Now, my drawing may not be so good, but what I can do is just count these so I can see, all right, the orange bar was split up into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 parts. What that means is that the orange line was split up into 10th size pieces, but the green bar that we start with here, it just stays. Let's see if I can do this. The green bar here that we started with, if I were to kind of transfer that down, again, I know it's not perfect, but it's showing as this section, which would have been 3 of our tenths. So, final answer here, what fraction of the orange bar is the green bar, or the light green strip is what fraction of the orange strip? It's 3/10 of it. So a little bit of work there, a little bit of, you know, I guess, working with the modeling there, but we can see how that's done and how it should come out. This one's kind of the same thing, so it's asking if the yellow hexagon represents 1 unit. Let's take that yellow hexagon, that's the top shape here. Hexagon is 6-sided shape. And we want to determine how much of that shape is the green triangle. So I take the green triangle and kind of fit it in there. And again, it's not going to be perfect just because of the way that the technology is working. But I can take that green triangle and kind of set it right there. But again, I need to know how many of the green triangles will fit into this hexagon. So if I were to do that, let's see if the technology will let me do it. So I've kind of copied the green triangle there. Let's see if it'll let me do even more. Oh yeah, there's another one. So I'm just going to take that one and just kind of fit these in, right? So I can fit 3 in there. And if you have the line still, you'll probably notice that these 3 yellow ones are also green ones. So I'm going to show that that is the case by taking the triangle here that I have. See if it'll let me do it. And what I'm going to do is bring it over here, but I'm going to kind of turn it so that it fits into the yellow right there. So let's see if it'll let me do that. Right, I think I got that to work there, and let's see if it'll kind of fit it. I didn't really rotate that so well, but let's see if we can do another one then. There's this one, and again, I want to rotate it so it fits into this shape here. You know, not perfect. I can kind of move that in there, and then once again, so I'm at 5 now, right? So let's see. Here's this one. So I got to fit it in there. Looks like it's kind of like this. Okay, so again, my drawing is not perfect. If you do this with the program that they give you, it'll probably fit in there much better. But I can see that it takes 1, 2, 3, 4, 5, 6 of the triangles to fit into one full piece, meaning that the hexagon has been split into 6 pieces. 6 pieces there. And one of the triangles is just one of the sixths. So one of the triangles that they gave us is only a sixth of the hexagon that they gave us. Okay, that's our whole lesson for 2.2. Hopefully you got the objectives down. If you do, the assignment will go very well. If there's any of those problems that you were struggling with, well, try some of the ones on the assignment. See if having a little bit more practice will help too. But that's it. That's it for this lesson.